Hello everyone. Today we'll be starting our discussion on reaction dynamics in solution. We have given you an overview on the reaction dynamics in gas phase where we discussed basically two models. One is the collision theory, which actually covered in the earlier course, but we talked about it very briefly. And the other theory is transition state theory, which is very widely used, and we showed that for very simple reactions these two theories are equivalent. Now those theories were developed, or the way we showed it to you is for gas phase reaction, but almost all reactions in chemistry and biology that happens actually in solution. We have to understand how actually what are the mechanism and what are the dynamics of reactions in solution. In solution, you have apart from the reactant molecules, you have solvents. So the solvents actually solvate the reactants. So you can actually imagine this reaction dynamics in solution. You can imagine it to begin with to something like that. Suppose these are the solutes, and all the solutes are basically surrounded by solvents. So the solvents actually influence the rates of reactions in many different ways. So, but in most of the cases, if these are not ionic species, and if there is not a large dipole which is created instantaneously, we'll see that the reaction rates are more or less equivalent to the gas phase reaction. The reason is these solvents does not directly participate in the reaction, because the solutes are only the participating candidates. And secondly, the thing is that the reaction potential between the two solutes is when they come close together. So that is the limiting factor, meaning unlike the gas phase reaction where actually it depends on the number of collisions, what will happen in solution, you can think it conceptually that these solute molecules or the reactants will actually diffuse, and so they will have some trajectory, and suppose after some time they actually diffuse this molecule, let's say A actually diffuse to the molecule B, and they are having now close encounters, and there can be multiple encounters between them, because now they are close and together they are surrounded by the solvent molecules. So the solvent molecules actually effectively provide a cage around the reactants. Now the interesting thing is that what I am saying, if we talk about it in detail, I have two reactants, so A and B, both are which initially were solvated, and then they should come close together so that they form a reactant pair, and this entire thing together is now solvated, and within this solvent cage they are having actually reactive encounters, and they will form products. And this is the overall mechanism of the solute solvent or the interaction between solutes in a solvent. Now we are not considering at this moment the reaction between charge spaces. We'll consider it later. Now diffusion is the key mechanism here, where actually the reactants are coming closer together. Now before that, let us have a slightly more discussion on what is this effect which I called as the cage effect. Now cage means it's a solvent cage around the reactants. Now there has been a very interesting experiment by Lineberger and co-workers, and what they showed is that if they actually were taking carbon dioxide as a solvent, and they took the reactant as I2 minus, and the reaction was something like that. They were actually shining light, and there is a photolysis or photodissociation which actually gives you I plus I minus. Now the interesting thing what they observed is that when they did this reaction, so initially I had I2 minus, which is surrounded by CO2, and the products are also surrounded by CO2, and then when you shine light, you generate I and I minus, but since they are still in the solvent cage, what can happen is that they can again react back, and means actually they can actually collide again within the cage, within the solvent cage, and they can again form the I2 minus. But when you have this, so the energy of the photon is actually released as thermal energy, because you are forming a chemical bond, and that energy is 167 kilojoule per mole. Now the interesting thing is that now it will depend on what is the size of the solvent cage, meaning if the solvent cage is small, what will happen, that excess energy may actually lead you to evaporate the solvent. So basically this solvent cage will basically evaporate, and the interesting thing which you will get is that this expulsion of the solvent may not be true for actually large clusters. So what Lineberger and co-workers did is that they were actually looking at this fraction, which is fraction of the molecules which are caged, and when they plotted this fraction of molecules, so here I am plotting this fraction of caged species. Now caged species means this is caged I2 minus. So it basically dissociates and it again reforms. So that caged species, so the fraction can be minimum can be 0, maximum can be 1, and then when they plot it with the precursor of this thing, like precursor I2 minus CO2N, because you can actually think that there is a cluster of suppose this is the I2 minus and this is the carbon dioxide which are surrounding the I2 minus initially. So I am calling it as a complex which is I2 minus and CO2N. So there are n number of CO2 molecules around it. So when I plot it along this n, the precursor complex, and where actually I am varying the n, so n will take of course integer numbers, and they found the experimental data showed something like up to n equal to 6, they showed that it is basically 0, meaning the species of the fraction of the cage species they are not getting, because the cage is actually blowing apart. Because this is too much excess energy, this 167 kilojoule per mole, that actually helps all these small number of molecules, that is basically translated into the translational kinetic energy of these CO2 molecules. So they fly apart, so they do not see any cage. But then once they increase the number of CO2 molecules, and then they see that when actually this number reaches something around say 16, above that you always see the cage is formed, meaning if the cluster size of this CO2 molecule, if it is greater than 16, the cage will be always stable, meaning 16, 17 or 9, 18, those many numbers or higher number of CO2 molecules, if they are present, the 167 kilojoule per mole energy is not sufficient to break that cage. But in between you see that up to 6 it is totally it can break, and in between 6 and 16 you have a more or less linear dependence of this fraction of cage species or cage I2 minus versus the these number of CO2 molecules that form this cage. So this actually was a very interesting experiment that showed how the cage effect actually influences the reaction, or how the solvent actually participates in this particular reaction. Now moving onward, so what is very important right now is that this was kind of a reverse experiment, in the sense that you initially start with a species and you photo dissociate it and you recombine back. But we are more interested in some general considerations, something like the picture I have drawn here. So I have A and B, and they are actually coming through diffusion, and then they are doing the encounter. Now the question is, for this we have to develop some diffusion control mechanism, which we will be discussing now. Now the question is, there is a mathematical model or a physical model to describe this kind of diffusion mediated encounters. But let us first discuss or extend our original discussion on diffusion and where actually we discussed the diffusion coefficient. What are the values of the diffusion coefficient? And if you remember our previous discussion, when we talked about this time dependent transport process, we talked about Fick's law, and there are two Fick's law. One was the Fick's first law and Fick's second law, and the Fick's second law basically tells you how the concentration varies with time, or how the density actually as a function of position and time. We are probably using some row notation or instant notation, so the notation can be slightly different. So as a function of time, how does it changes? And then we found that the time derivative in of the concentration gradient, how it changes over time, is basically the equivalent to the spatial derivative, and they are connected to a constant which is the diffusion constant. And that was, if you remember, that was Fick's second law of diffusion. Fick's second law of diffusion. Now moving on, if we can actually integrate this equation. I will not show you how the integration is done, it requires some knowledge on how to integrate this kind of equation, because actually n star is dependent on both z and t. So you have to first make, you cannot do a separation of variable here. So if we move on, so I am just writing the solution for you. If I want to know how basically this concentration, which is a function of space and time, is changing as a function of space and time, and particularly as a function of time, how it is changing at a particular location. So what we will get is basically we will get something like 1 n over a and 2 square root of pi into pi dt, and then we will have e to the power minus z minus z0 squared by 4 dt. Now what is z0? If you remember your old model that we kind of developed, we said that we are considering the flow along the diffusion along z, and then we considered a plane at a location z0. So this was at z0, and then we considered the flux through the surfaces. If you remember that there was an upward flux, that there was a downward flux, and that's how we calculated it. And we said that within the mean free path then there will be some flow of the molecules, and we did all these nice calculations. Now what this equation shows is that at suppose some z0, okay, so if we consider that to be the origin, and then if we just plot this quantity, this n star, as a function of say of course z, and suppose z0 is the origin. Now how it changes with respect to time. Now if I plot it with respect to z only, so it is a Gaussian. As you can see, it's basically y as a function of x is in this equation, it is basically e to the power minus some constant into x square. Now that's a Gaussian function, so, and which is centered around z0. So it will look like something like this. But with respect to time, if I now plot the another Gaussian, so as you can see, the t is here. So t is basically connected to the standard deviation or the width of this Gaussian. So if I have more and more t, what will happen here? This distribution will become wider and wider, but it will be still a Gaussian distribution. So as we see that with respect to time, this distribution is basically spreading out, which makes sense, because it's basically a time evolution of the concentration profile, and eventually the concentration should become very much flat when there is no flow. Now the interesting thing is we can actually, if you ask this question, what is the mean position of z, or what is the what are the if I just ask this quantity, what is the average value of this z? So if it is a one-dimensional diffusion, which we considered, and if we ask this question, what is the mean position, that mean position will be 0, because the particles are equally there is an equal probability of the particles going towards right or going towards left. So on average, on statistical average, the mean position will always be 0. So if we can actually, instead of the mean position, we can actually calculate the mean square position, which will not be 0, and then to get a value of the mean position, we can actually take the square root of that, and which will be nothing but by definition is the root mean square position. Now z and x are arbitrary, so we could have written it as x also, but I am following the older notation which we were following. And if you calculate that, so let us just try to calculate it, how to calculate this z square average. So z RMS, which is the root mean square position, and we have to take z square and then half. But let us first calculate the z RMS squared, and then we will take the square root. And as you can see that if we calculate anything's average value, it will be nothing but I have to take the position, which is z minus z0, and then I have to multiply by the distribution function and then integrate. In this case, the distribution function is something we already talked about. It is 1 over 2 square root of pi dt, and then we have e to the power minus z minus z0 squared divided by 4 dt. And then we have to integrate this quantity, which is going from now z is a one-dimensional quantity, so it can go from plus minus infinity, and we'll have a dz. Now you see here, first the variable here is z, but here I have z minus z0, so you can easily do a transformation. Suppose I tell that z minus z0 is, let's take some variable, let's say y. So dz is nothing but dy, because z0 is a constant. So I can just write it, and also when z tends to infinity, y also tends to infinity, and if it is minus infinity, y also tends to minus infinity. So the limits are same. So I'll just rewrite it like this. So I will have y square, and this is a constant. So this constant we can first take out of the integration. So I'll have 1 by 2 inside square root I have pi dt. So I'm actually integrating over space, so all the time part actually comes out. So it's a special integration, and then I have minus infinity to plus infinity y square e to the power minus y square divided by 4 dt into dy. Now this is an even function of y. So instead of writing the limit as minus infinity to plus infinity, we can write it as 2 times 0 to infinity. So this integration will be 0 to infinity with the additional 2, and that 2 actually gets cancelled with this 2. So we'll have 1 over square root of pi dt, and inside bracket now I have y square minus e to the power minus y square times e to the power minus y square by 4 dt into dy. Now actually we can use the gamma function, and if you remember, we wrote the gamma function as e to the power minus ax x to the power n minus 1 dx. That integral between 0 to infinity is nothing but gamma n by e to the power n. Now here, as you see that I have here y square, but I have here y. So I have to write this dy in terms of d of y square. Now you know that d of y square is nothing but 2y dy. So I have to actually write it as 2y dy. So let us just write it. So I will write it as 2y dy, so that in the next step I can write it as which is d of y square. Now if I have 2y dy, I have taken one y from here, so this becomes the y square becomes actually y, and then I have e to the power minus y square by 4 dt. I have integral 0 to infinity, and but I also have a 2 extra 2, so to account for that I also have to divide it by 2. So that's how the integration looks like. Now still, so what I'm going to do is basically this y, I'm going to write it as y squared to the power half, and y squared to the power half can be further written as half is 3 by 2 minus 1. So now actually it forms, it looks like a gamma function, where you can think the x here, the y square is basically x here. You look at this form of this gamma function. So the variable x is basically y square in our equation, and the constant a is nothing but 1 over 4 dt. So you can easily figure out what is the value of the gamma function. So there is an integral 0 to infinity, and the constant 1 over 2 square root of pi dt. So let us evaluate now the integral using the gamma function relation. So what we got is we have 1 over 2 square root of pi dt, and then this is nothing but gamma 3 by 2, because you can easily look at the gamma function here, and it is e to the power minus ax, x to the power n minus 1. So x is just y square, so it is n minus 1 is 3 by 2 minus 1, so it will be nothing but gamma 3 by 2 divided by a to the power n. Now a is as I said, it is basically 1 over 4 dt to the power 3 by 2. Now what is gamma 3 by 2? So gamma 3 by 2 will be basically gamma n is n minus 1 gamma n minus 1, so it will be half gamma half, and because actually let me actually write the value of gamma function here. So gamma n is basically n minus 1 into gamma n minus 1. That's how we have to proceed, and gamma half is basically root pi. So now with the analogy we can show that gamma 3 by 2 is nothing but half gamma half, which is half into root pi. If you put these values, you can see what is the value of the integral. So as you see, I have 1 over 2 pi dt to the power half, and then I have half here, and I have pi to the power half. So this pi to the power half will basically cancel out with the other pi to the power half in the denominator, and then what I have is 1 over 4 dt. So I can actually take it up, so I'll have times I'll have 4 dt to the power 3 by 2. Now so as you can see that I have 4 to the power 3 by 2 and 2, so that will basically cancel out. 4 to the power 3 by 2, so 4 to the power half is 2, and 2 cube is 2 cube divided by 2 is nothing but 4, so we'll have 4 in the denominator, and what we have here, there is one half here, so that 4 at that half becomes actually 2. Let me actually rewrite it once again. So what I have 1 and 2, so I'll have basically 1/4 times 4 to the power 3 by 2. So together actually I'll get a half, because 4 to the power 3 by 2 is nothing but 8. 8 by 4 is half, and then what I'll have, look at the pi's. pi's will get cancelled because it's pi to the power half, and here pi to the power half, it will get cancelled. Now I have dt to the power 3 by 2 and dt here. So what I will have is just simple dt here. So what we see here, so it will be not 1 over 2, it will be just 2 dt. So it is basically 8 divided by 4. So ultimately I am getting 2 dt, and that was basically ZRMS squared. So ZRMS will be nothing but square root of 2 dt. So this basically shows you what is the mean square displacement of the if a particle is diffusing, what is the mean square displacement. Now this result will be very useful to discuss the subsequent discussion, and which will be very important to calculate the reaction, the rate law or the rate constant in solution. Now let us first discuss the model for, suppose I have a Brownian particle and how it is diffusing inside a solution. Let us first try to formulate that. Now let us discuss what are the dynamics of a Brownian particle in a solution. Now to approach the problem, we will just apply the laws of motion, and we know that acceleration, mass times acceleration is the force, and then we can actually say that if the particle mass is m and the acceleration, we can write it as dv dt, that is equal to some frictional force which will be dependent on the velocity, because as it moves, actually it experiences a friction from the solvent molecules, and that force actually acts in the opposite direction of the movement. So if the frictional coefficient is constant, which we write it as zeta, so I am writing a negative sign for that. And then there will be also a random force, which is of course time dependent force. Now this random force is very much stochastic in nature. This is basically solvent molecules are moving around, and for that actually this Brownian particle receives a continuous thermal kick from all the direction. Now what we are interested in is an average force. Now average means actually it's average, if I talk about one particular particle, it is basically average over different position, or if you can think about an ensemble of particles, in that sense also it is, we are taking basically average of position. And if we think that this random force is not dependent on position, then we can always say this average value of this force is going to be 0. Now we can right away take the average of this equation and write m d v average dt is nothing but minus zeta into v average. Now these are all identical particles, so even if I take an average, so m actually comes out, and because m is a constant, it is mass, and zeta is also a constant. Now we can right away integrate it. It's a very straightforward equation. So it will be dv by v will be minus zeta, let us just do it. So dv by v, the average of v, is nothing but minus zeta by m into dt. And now we can actually integrate this equation, and assuming that at time 0 the initial velocity or the initial average velocity was like v0. So it's average of v suffix 0, that corresponds to time, and at any arbitrary time the value is v. So we can easily see that v will be nothing but v0, the 0 time velocity, times exponential minus zeta by m into t. So what we see that the velocity actually drops from the initial velocity v0, and at infinite time it becomes 0 with a time constant. If we actually write this equation as it's nothing but some kind of correlation function. So if we write it as t by tau, then the time constant for this exponential decay, as you can see, is nothing but m by zeta. So that's with this time constant, basically the initial the velocity actually drops from its initial value to 0. Now the question is, how do you calculate the mean square displacement from this equation? Now already we know that, in order to calculate that, we'll just use the formula for the diffusion coefficient, and then we'll just write the mean square displacement, which we had already calculated, the z RMS square, but instead of z we'll be using the x notation, and then we'll be using this connecting the mean square displacement to our to the time, basically with the diffusion coefficient. Now the problem here is that we have solved it with respect to the velocity, but we are more interested in calculating the position of the, because what will eventually happen is that we'll calculate what is the mean square displacement in terms of the diffusion coefficient, and then we'll want to see that for a Brownian particle, and then we want to see how this particle actually changes its position, because it is ultimately the diffusion that is basically mediating the reaction in solution to happen. Now in order to do that, instead of writing it as m dv dt, we'll just rewrite it in a slightly different way. We just have to write it in terms of position, and you already know that velocity is nothing but dx dt. So if you follow this equation, so this is nothing but this equation, I forgot to tell you, this is known as the Langevin equation. And here the assumption here is that this Brownian particle is much bigger than the solvent molecule, so that the solvent is treated as a continuum, and that's why the forces which are originating in the solvent is basically stochastic, and then if you take an ensemble average, it's basically washes away. However, if the particle is very small, for example, if you have a, let's say, nanoparticle which has a dimension of few nanometers, which is diffusing in, say, water, then actually particularly in a very short time scale, the diffusion or the forces will become very important to control its trajectory, and then you cannot actually average out the forces, because the particle size is almost equivalent to now the solvent size, so you cannot actually use a continuum solvation model to describe this phenomenon. Now we are not discussing that, we will just describe everything within the context of Langevin model. Now I can actually write now the force equation. So that was basically, if you remember it, that was basically mass times acceleration, and acceleration is nothing but, you can just write it like this, x into d dt of dx dt. So if you follow this one, so I had basically multiply, what we did here is that we actually I am going to multiply both sides by x, so we can actually show it in the next step. So let us first start with the original equation, so that you don't we can follow actually every step. So we have actually a force, okay, and the force was basically random, so we can actually from the beginning ignore that force, because you are anyway going to average it, but I am keeping it for the time being. So I have mass times acceleration. I am writing the old equation once again, is basically related to balanced by a opposing frictional force which depends on the velocity, and plus random force which is f of t. Now I am multiplying both sides by x, as well as what I am doing is basically writing v as dx dt. So what I will have is m, I am multiplying by x, and I will have d dt of dx dt, and then on the right hand side I have minus zeta, and then I have x times, instead of v I will write dx dt, plus the random force, but I multiplied both sides by x. So now look at this term, why I multiplied it by x. So if you take say x into dx dt and take the time average of that. So then what you will get is that x is the first function, dx dt is the second function. So the first function will be dx dt times dx dt, so it will be dx dt squared plus I will have here x into d2x dt2. Now what we have got here, you see here, it is basically x into d2x dt2 times an m. So this guy will be nothing but this term x into ddt of dx dt is nothing but x into d2x dt2. So we can actually right away replace it we can write it as it is nothing but ddt of x into dx dt minus d2x dt2. So I am just multiplying, there is an m mass, so I am just writing, I am not keeping it within the bracket, so I am just multiplying it by the mass. So it is into dx dt whole square, that will be equal to minus zeta into x into dx dt plus x into f of t. So what I have done, I have actually cleverly used this equation, because remember that what I eventually need is to get an average value of x squared. Now let us see how we can actually proceed it, but before that let us take first the ensemble average. Now if you do the averaging, so which you could do earlier, but I am doing it right now, what we get is basically m and then average of this quantity, which is ddt of x into dx dt. That will be equal to, I am writing this term first, the zeta, the frictional term, which is zeta, and then average of x into dx dt, and then I have an additional term here, I am putting it on the right hand side. So that will be a plus sign into m into average of dx dt squared. And naturally this term, I know that if I take the average, it will be automatically 0. So what is interesting now is basically I have m times ddt of x into dx dt, and now you see that what is dx dt squared. Now dx dt square is dx dt is v, right? We actually wrote it very earlier. So here, so this term is nothing but mv square. Now mv square is nothing but, again it's a kinetic energy, and for a particle the kinetic energy expression is half mv square. And we know that half mv square, according to the equipartition theorem for one dimensional particle, it will be nothing but basically equivalent to the thermal kinetic energy, so which is the half kVt. So mv square will be nothing but kVt. So I am going to replace that term by kVt. I can make further simplification. I have m times ensemble average of ddt, a time derivative of x dx, that quantity. So then actually I can do the time derivative later, and I can first take the average, because this average is basically a special averaging. So what I can write is, instead of writing this term like this, I could have actually written it as m times, I can actually divide both sides by m. The m I am not writing right now. So what I am saying is that it's a ddt of average of x into dx dt, that quantity is basically minus zeta by m, and I have x dx dt plus I have m, I divided both sides by m, and I know that dx dt whole square is nothing but v square, and the average kinetic energy, I should have actually used average sign here. So the average kinetic energy is a half kVt. So the twice the kinetic energy, which is basically mv average v square average, is basically kBt, and I'm not writing the m because I have divided both sides by m. Now this equation we can actually solve, and then what you will get is basically where if you just write this x into dx dt part, which we actually solved earlier. So that will be already what we figured out from the Langevin equation. So that we can actually write as e to the power minus, if you remember correctly, so x into dx dt was basically your v. Now we can integrate this equation because as you can see here, it's a time derivative of some quantity which is x into dx dt is equal to some constant times that quantity plus kBt, and if you write the solution, it will be basically x into dx dt. The average quantity of that is nothing but a times e to the power minus zeta by m into t plus kBt by zeta. Now you can always check whether this equation is correct or wrong by just differentiating this equation with respect to time. So if you take the time derivative, as you can see here, so I'll just basically pull out one zeta by m at the front, and that will be minus zeta by m into a into e to the power minus zeta m by t. But and then I'll have actually time derivative, so this part will be 0, the second constant, and then you can write this a into zeta minus zeta by m into a into this e to the power minus zeta m by t again as the old function, and you can easily get back to it. So this is just to check whether this integration is correct. Now what we have received, I mean what we have done so far is basically we can just now write x into dx dt as now this is very easy to rewrite because remember that all we wanted to do is get an expression for x square average, the mean square displacement. Now if I take a time derivative of that, so what I will get is so if I take a ddt of this quantity, so that will be nothing but ddt of x square. I can write it because it's just a spatial averaging, and then that is nothing but as you can see, it is 2x dx dt. So it is nothing but 2 times x into dx dt. Now this is exactly what we have solved for. So I can actually write this quantity x into dx dt as nothing but half times ddt of x square average, and that's what we are going to evaluate, the mean square displacement if the choice of the axis is x, e to the power minus zeta by m into t plus kBt by zeta. Now I have already kind of solved it. So what we could write actually now, we can actually, to make things a little bit simplified, as you can see I have actually a into so we can actually make first the initial conditions here, in the sense that I can say that when t equal to 0, I can actually choose an initial position, in the sense that if you remember our original description of diffusion, where we wrote this figure that I have my initially actually I am starting from z0. Similarly, if I take here actually I was using z notation, right now I am using x notation. So x square average, so that quantity we are going to actually calculate eventually. Now instead of choosing the origin to be x0, I can actually set x0 to be 0, because that is purely arbitrary. So if I do that, which means actually at t equal to 0, x is equal to 0. Now you can actually put back in your original equation, so the left hand side becomes 0, and this becomes basically e to the power minus zeta m by t, that becomes 1, so it is e to the power 0. and then what I get is nothing but I'll get from here A is nothing but minus kBT by zeta. So I can actually rewrite this equation now as half times ddt of x square average is nothing but I can take kBT by zeta common, and I'll have 1 from this term, and there's a minus sign for A, so it will be minus e to the power minus zeta by m into t. Now exponential terms I can further approximate, like e to the power say x is 1 plus x square by 2. That way I can actually expand it, and I can think that this mass of the particle is, if it is much heavier, then actually I can truncate this series up to few terms. So I am considering it up to the second order term, which is the x square term. So let us just write it. So I'll have kBT by h 1 minus, now the first term is 1, and then it is e to the power minus zeta m by t. You can actually take the variable itself to be minus zeta m by t. So the next term will be nothing but x, and x is nothing but minus zeta m into t, and then I have x square by 2. So I'll have half x square is minus zeta m by m into t whole square. So the minus will be plus. So I'll have basically zeta square m square into t square, and I'm basically truncating it. So this is basically an approximate value for this, and what I get here is, after as I can see here, this 1 actually, I had an 1 here, so this is 1 minus this thing. So let me actually rewrite it once again. So I have 1 minus, and this is the exponential series, and I had kBT by zeta. So what I see is that this 1 will cancel with this 1, and then I have the second term. It is basically minus zeta by m, but I also have a zeta here. So overall what I will get is, as you can see here, so let me just rewrite it. So I'll write it as ddt of, let me actually write it like this, ddt of x square average is nothing but 2 times I have kBT divided by zeta, and inside I will have zeta over m into t, and then I have minus and minus, so this will be plus. I have 1 minus and 1 plus, this will be minus half, and then I have zeta square divided by m square into t square, and then what you can do,